Okay, so we have figured out how a certain class of solutions behave at the origin. And now let's look at another class of potentials, which are V of R goes to 0 as R goes to infinity class of potential. And we will look at what the solution looks like asymptotically. So can somebody tell me, give me an example of this kind of potential? So what happens to your weight when you go far, far away from any astronomical body?
It goes to 0.
What does it say about its potential?
Increases. I don't know. Potential. How could I forget this?
So if the force is 0, what happens to the potential?
It becomes 0?
It becomes a constant.
Yeah.
And of course, you can set that to 0, right? Because we know that physics is invariant under whenever you add a constant to potential energy, it does not change anything.
Mm-hmm.
Right? So, V of R, the gravitational potential, as we just talked about, is 1 over R. What happens to it as R goes to infinity?
It becomes 0. As R goes to infinity. Yeah.
So this is so gravitational force as well as the Coulomb force are important examples of this. Can you now give me some, well-known physical system where this is not true? Where the potential energy doesn't go to 0 as the distance from the center of the system increases?
I don't think I have one in mind right now.
Anyone else wants to try? Think physically. You even gave me the answer to this before. It was the wrong answer to the question I had asked at that time, but you have told me about a physical system, which is the correct answer to the question of a potential which does not satisfy this.
Is it the oscillator thing?
Yeah, the spring, right? So we know that. What is for a simple harmonic oscillator, what is the potential? What does it roughly look like? Some constant, positive constant times x squared.
X squared, yeah.
And the three-dimensional case would be, some positive constants r squared, right?
Oh,
so
yeah.
Here, if I do a two-dimensional version of this, as r increases, your potential energy increases, right? It doesn't go to 0. It's a quadratic potential. So that's an important class that is not included in this, okay? Okay, so now if I do this, if I take r to infinity, then V of R goes to 0, but our angular momentum barrier also goes to 0, right? Because it's 1 over r squared. Right? So this also goes to 0. So all we have left are the differential, the derivative term and the energy term. In the energy term, we can redefine the energy. We can define kappa squared to be minus 2me over h of r squared, okay? Now, for bound states, and here we are interested in bound states, what is the sign of energy? The total energy of Earth around the solar system, is that positive or negative?
Positive.
Okay. What is your energy? Is that positive or negative? Sitting on the Earth, your gravitational energy, total gravitational energy, say. Suppose you're jumping up and down, so you have some kinetic energy. Of course, kinetic energy is just kinetic energy, but your potential energy, is that positive or negative? If I set the value of the potential to be 0 at infinity, which we are doing, right? Then as you come towards the Earth, is your potential energy positive or negative?
Negative, I think.
What do other people think? Is Shujosh's potential energy positive or negative as he is sitting on the Earth?
Negative.
Negative, okay. Very good. So E for bound state is negative, right? Because energy consists of kinetic energy and potential energy. Remember that you had to find in your first year mechanics, the escape velocity from the moon. Do you remember this?
Yes, sir.
And you were just given G of the moon. What did you have to do? You said that, okay, the potential energy of the object at height h was mgh, right? Of course, here what we're doing is that we are calling it, we are setting h equals to 0 to be to be infinite, to be the 0 energy, right? Because that's and remember that you had to, you were saying, okay, what we want is that, we want to equate, what was the argument that went like? The idea was that, okay, so what is happening here? Sorry? Moon?
Sir, we used to equate the total energy from.
We used to equate what?
Like the kinetic energy is equal to potential energy.
Yeah, except here, we have set, if so, this is the moon, right? So this is the moon, and this is also not exactly the correct expression, right? Because it's saying that G is constant, whereas G is actually. Do you remember? I've forgotten. Okay, I think it has went something like this. Let me try. Okay, the force on the object is minus G moon's mass times the object of the mass divided by r squared, right? And then so the potential energy is going to be minus f of, say, d of x, right? Say we are bringing the object in from infinity, but we are bringing it in the radial direction, suppose, okay? And so r goes from, say, the radius of the moon to infinity, right? And then we have minus and there we have plus r in minus 2 plus 1 is minus, so there's going to be a minus sign in the end, right? There's a minus sign, and it's going to be G M M over R, right? Do you agree?
Yes, sir.
Are you sure?
I feel like that's what I remember, but
No, it's not about remembering. We are trying to derive it. So there's a minus sign here, and if has one, if has a minus sign. So there's a minus minus. Is there a minus sign here? No, there's no minus sign here. Okay, there's no minus sign. This is work done, right? This is work done, and work done is force times the E, displacement, right? So if I take so there's a minus sign in F, which is this minus sign, and if I take the integral of 1 over R squared, I get minus 1 over R, right?
yeah.
So so we get over here we get this, and first we just put R here, and we have R this. I feel like we are we are missing a sign because F is attractive. So yeah, this is going to be positive work, right? Because we are pushing the particle in the direction of the attractive force. But if you were taking the particle, say from R to infinity, then we would have a minus sign, right? And suppose we are doing that, minus sign. And so this is, so we are pushing it from R to infinity, right? And then we have a minus sign here, a minus sign from the integration, and then we have a minus sign here, and then here we have, yeah, I don't want to spend too much time on it, but right, so then we have, then we do, if we do this, then of course we are doing work, and then we get minus minus plus GM big M R, right? And then what we did is that we said, okay, this is going to be half MV escape squared, right? And then what is this? This is M times big G big M by R. So then is this G?
Feel like it is. If we no, I don't think so.
What is,
I think
MG's weight, right? So
sorry?
MG's weight, but shouldn't it be potential energy? So
Sorry, Moon, what are you saying? So okay, G is F over M. Right? Oh yeah, sorry, this is not, yeah, there's an R here, right?
yes.
Yeah, this should be GR, right?
Yes.
Do you agree?
yeah, for the dimensions.
Yeah. Moon, do you agree?
Yes, sir.
Okay. So yeah, because of that, yeah. Anyway, I make some mistake, but what we will do is that we basically have to cancel M from both sides, and then we get V escape is going to be 2. I think it's GR, and then it's a square root, right? Okay, so why were we doing this? I was just trying to argue about bound states and how they have negative energy. And I was trying to justify why we have to assume that the potential, if we assume the potential energy is 0 at infinity, then our potential energy near the Earth is negative, and therefore for bound states, the natural the total energy is something negative. Okay, so let's get back. So in this formula, E is negative, and therefore this is positive, right? And therefore K squared is positive. So that means that we have solutions to this, but and the solution that is relevant for us is U E of R is e to the power minus KR, right? So there is also another solution with a plus sign here, but we are not taking that because then our wave function will diverge at infinity, and then we won't be able to normalize our wave function, right? So for such potentials, that is potentials, which go to 0 in the limit r goes to infinity, as well as potential which go to say 0 as r squared, the potential goes to 0 as r goes to 0. For this class of potential, we can write our radial wave function to have a part like this times e to the power minus rho omega of rho, where omega of rho is a well-behaved wave function. Rho, we have defined rho to be, say, KR. And then we can now plug this into our differential equation, the full differential equation that will give us a differential equation for omega. And that omega is d squared omega d rho squared plus 2L plus 1 by rho minus 1 d rho by d omega by d rho plus v over e minus 2L plus 1 by rho. Okay, so this is the differential equation for a very general class of systems in which, for example, the Coulomb potential is included. So in the next class, we will solve a system where this equation is valid, okay?